So I'm designing a 2D rendering pipeline for my game engine. Technically, I already have one. I'm using it to draw the editor UI, but I also want to go through some design decisions and like how I ended up with the current vertex layout. Here, a quad contains of 4 quad vertices, and it is rasterized as 2 triangles. This is enough to cover pretty much all kinds of 2D primitives, such as rectangles, sprites, ellipses. We can even apply some border radius with some math in the fragment shader. Note that I am not trying to present this as the best solution or anything, I just want to share how I landed on this current vertex layout. I'll make another video on the CPU side of things, such as mouse picking and sorting by depth, but today we are talking about the GPU side where we use a single pipeline to draw a wide range of 2D primitives. First of all, let's justify 2D batching. The goal of batching is to minimize draw calls and pipeline state changes. Draw calls are pretty much the CPU sending a request to the GPU to render vertices through a pipeline. Let's say we want to draw the following 2D primitives in order. If we have a separate vertex layout for drawing triangles and circles, what would happen is that we have to first flush the current triangle vertex batch, and then we start a new circle vertex batch, as well as switching from the triangle pipeline to the specialized circle pipeline. Similarly, when we want to draw the following square, we will first have to flush the current circle batch and then start a new triangle batch, because a square is just 2 triangles. If each 2D primitive uses a different vertex layout, we will have to submit draw calls every time we context switch. Some renderers will draw a lot of triangles to approximate a circle, but this only works well if the circle is small or you approximate the circle with a lot of triangles. Later we will discuss how to draw a circle without the triangle fan approximation, but let's start with something easy. For something as simple as a rectangle, we only really need a position in 2D space and a 32-bit color. The reason we don't use a vec4 for color is because a vec4 is 16 bytes, whereas a 32-bit color is just 4 bytes. We can let the GPU perform the interpolation, and generally we don't need that much precision for color. Drawing a rectangle outline is also pretty useful for debugging. For outlines, I just draw 4 rectangles and call it a day. Next up, we have images. This is where the UV members of the QuadVertex comes to play. UV is just a normalized coordinate system for texture sampling. I'm using Vulkan, which uses top left corner as UV origin. The 4 UV corners are interpolated, and inside the fragment shader, we can use the UV coordinates to render a full image or just a region of that image. In this case, the color bits can be used to tint the image, or we can just leave it as white to draw the original image color. Up until now, we have used 20 bytes for a quad vertex, and this is actually the same vertex layout as what Dear I'm GUI uses to draw the UI. You could override the vertex layout in Dear I'm GUI, but by default it uses the exact same 20 bytes. vec2 position, vec2 UV coordinates, and a 32-bit color. My quad vertex uses one extra field, a 32-bit control flag. Currently, I reserve 4 bits of the control flag for selecting the image. Different graphics API versions and GPU drivers will give you a different limit for simultaneous texture samplers, but 16 image slots is pretty common. In modern Vulkan versions, you can actually use bindless rendering to completely bypass this image slot constraint, but for other graphics APIs such as OpenGL, you have to respect this limit. Alright, so some image slots could hold a texture asset from your game, and some image slot could hold a texture for your font atlas, which is used for text rendering. This also means that we can draw flat color rectangles, images, and even some basic font rendering without context switching, because they have the same behavior inside the fragment shader. I call this behavior the quad mode, and I reserve 4 bits of the control flags to describe what mode we are using. I don't think I will ever have 16 different modes, but we only used 8 out of 32 control bits. More importantly, with the addition of mode bits, we can finally render an ellipse. To draw an ellipse, we will define another quad mode so that the fragment shader will try to fill an ellipse bounded by the 4 quad vertices. Here we want to suppress the alpha opacity for pixels that are too far from the origin. But what is this origin? We can't use the center of the UV members of the quad vertex because it is used to sample texture, and it may not be normalized. We want some sort of local UV that is normalized within this quad. If we tried adding a local UV member to each quad vertex, we end up using 8 extra bytes per vertex. So instead, I am going to use the first 2 bits of the control flag to store the local UV. Inside the vertex shader, we will do some bit masking to extract the first 2 bits and output the local UV as a vec2. This means that each fragment shader invocation will see a smoothly interpolated local UV coordinate. The only thing left to do now is to check how far the local UV of the fragment is away from the origin. If it is further than 0.5 units away, we suppress the alpha channel of the fragment. In practice, we would use some smooth step function to nicely filter out the opacity around the edges. A circle is just a special case of the ellipse where the quad aspect ratio is already 1. Before we discuss how to draw with a border radius, let's make use of the remainder of the control bits. Currently we have used 10 bits, and I want to encode 2 normalized ratios inside the control flag. If we use 10 bits to represent a normalized ratio, we can express a ratio at around a precision of 0.001. So how is this useful? The interpretation of these ratios depend on the quad mode. For example, if we are rendering with a signed distance field font atlas, we could use 1 ratio to decide how much we need to scale the signed distance. Okay, but what kind of quad mode would require 2 ratios? To render a quad with border radius, we would obviously want to configure the radius of the border. Let's use 1 ratio for this. At 0, we are basically just drawing a rectangle, and at 1, we will be drawing a capsule shape. However, we are still missing the aspect ratio information, and this is where the second ratio comes in. Aspect ratio is usually expressed as width divided by height, and it is obviously not normalized, so at the CPU side, we need to define an upper limit. If the height is 0, we will simply use the max aspect ratio. Since we have an upper limit, we can normalize this aspect ratio and encode it inside the control flags. At the GPU side, the fragment shader sees the border radius quad mode and then restores the aspect ratio. Obviously, this will require your fragment shader code and CPU code to agree on the interpretation of the ratios under each quad mode. Now the fragment shader can see the inner and outer regions based on the border radius and aspect ratio information. Finally, we can check how far the fragment's local UV is from the origin of the border square. This coordinate system is different from the local UV. We have already applied the aspect ratio, so we keep the height at 1 and scale the width based on the aspect ratio. So yeah, that's about it for the quad pipeline design. I have been using this 24-byte vertex layout for a while now, and I am kinda happy with it. The only technical part is really just how we partition the control bits to encode as much information as possible. I may end up changing the partition as the engine grows, but that's about it for today. If you're interested in more game engine design and rendering stuff, please consider subscribing, and see ya.